Okay, this is section 4.5, part 2. Hopefully my voice will last. So this is called differentials. A differential, let y equals f of x be a differentiable function. The differential dx is an independent variable, and the differential dy is dy equals f prime of x dx. This is just another way of writing our derivative. Take a look. So y equals f of x, dy dx would equal f prime of x. Therefore, multiplying both sides by dx, dy equals f prime of x dx. The reason we do this is because if I want to use a tangent line again to find an approximation, if I take my derivative, which is change of x, change of y, my slope of my tangent line, then given a particular change of x for the function, I can find a differential or an approximate change of y for the function. Now, delta y is the exact change as the function moves from x to x plus delta x, but my differential dy is an approximate change in f of x for a given x value and a given dx, which is the same as delta x. That's not multiplication, that's just writing it two ways. Okay? So we're going to use this differential again to approximate a given change in a function over a particular change of x. So let's try one. Finding the differential dy. Find the differential dy and evaluate dy for the given value of x and dx. So here's my function. I'm going to find the differential when x equals 1 and my change in x is 0.01. So first we find our differential equation. Dy equals our derivative, just simple power rule, times dx. Now I'm going to evaluate this when x equals 1 and dx equals 0.01. So my differential, 5 times 1 plus 2, and my differential is 0.07. So on this particular function, when my x value moves to the right 0.01 units, my function will increase by approximately 0.07, which is an approximation for my actual change in y. Okay, let's look at another one. Okay, so another definition. So the differential is our estimate of change. This is just notation. I have not seen it written this way very often, but if f of x is differentiable at x equals a, then the approximate change in the function value, that's my y change, when x changes from a to x plus dx, is the differential, again, normally written dy, of f prime of a dx. All right, let's try another one. So we're estimating change. The radius of a circle increases from a equals 5 meters to 5.1 meters. Use a differential of a to estimate the increase in the circle's area. So again, the function I'm interested in is area. So first thing I need to do is write an area function. So area equals pi r squared. I'm looking for the increase in a, or dA, when I know the change in the radius. So again, I'm going to write my differential, dA. Go ahead and do your derivative, see what you get. So 2 pi r dr. I know that my radius was 5 to begin with, and I know that dr, or my change in my radius, was 0.1. So plugging those values in, 5 for r, 0.1 for dr, I find that dA is pi meters squared. So when I have a circle with a radius of 5 and I increase that radius by 0.1, the area's increase is pi. And that's it for our video. Pretty simple. We'll do some problems together in class.